my former university. And then I moved, and my lovely colleagues carried on the work, so they got to the conclusion. So I really need to thank them for the final results we're having here. I'll talk you today through first the process that we're using, and then the results that we're getting. So the agenda, is it working? Okay, just go with the arrow. So this is the agenda. First, we'll see why we need transparent electronics in general, but also in particular why we need thermocouples. And then the step is quite small to get to transparent thermocouples, and how we mean to employ them, how we need to fabricate them, and then the characterization of the single layers from the point of view of the transparency and from the point of view of their conductivity. And then in the end, we will fabricate some thermocouples and characterize them from an electrothermical point of view. The motivation behind it is that, of course, it's a very high topic. The transparent electronics is nowadays almost everywhere. So if you think about flexible photovoltaics or touch panels, or also OLEDs, which are great now for lighting applications, but also for displays and so on. You would want to have some conductive layer or semiconducting layer that is also transparent at the same time. And that's not an easy task. In most cases, the material that is being used is the ITO, indium tin oxide, which is a beautiful material. It's a conducting oxide, but it's also a bit brittle, which means that you cannot really affect it so much. It's also fairly expensive because of the price of the indium, and it's not easy to scale up in let's say, cost-effective lab facilities. We're also thinking about applying transparent electronics to objects, smart objects that one can print, for instance, with a 3D printer at home, and then make them smart, integrating some electronics into it. Now, as I said, we want to have transparent thermocouples, but first we want to have thermocouples, and that's because it's not changing the slide, I'm sorry. Okay. And that's because thermocouples in general are a very sexy element, because they're at the same time a differential temperature sensor, which is self-powered, and it could be also an energy harvester. So you can imagine that two characteristics put together can lead you to have either a device that is able to charge an accumulator of charge, or a device that is able to power itself and to give a measurement. Also, it is quite a flexible approach. It is quite a flexible device. In this case, with flexible, I mean that it has many capabilities. It could be used for harvesting an in-plane heat flux, and in this case, I, for instance, would be very happy of having a material with a low thermal conductivity, because we do not want the heat to go from one side to the other. So being able to isolate the cold from the hot side would be very nice for us. Or the out-of-plane heat flux, which is like the classical approach for thermocouples, like the conventional ones. When I say conventional thermocouples, we mean solid-state materials, which are very established in now almost for 50 years. What you do is you use normal lab facilities, which are characterized by low pressure, high temperature, and everything that we're aware of in typical silicon and semiconductors technology in general. But that's not what we're aiming for with print electronics in general. We want to have something that is cost-effective and that is potentially doable at home. Also, we have another major drawback of this technology, which is that if we want it to be transparent, that's simply not going to happen, because those are semi-metals and they are opaque and reflected in most of the spectrum. So what we're doing is migrating towards nanomaterials that we'll see not in the next slide, but the following one, and that we must be able to deposit them with very scalable and cheap techniques. With very scalable and cheap techniques. What we employed in this paper particularly is the spray deposition. We use the simple spray deposition method. There are several ones, and we went for the air-assisted one because we were not looking for particular uniformity of what we were about to have. Spray deposition means that we have a solution. In this solution, we have a dispersion of our material that we want to deposit, and then we use the kinetic energy of air to atomize this material and to direct it towards a substrate. Now, it is a coating technique, which means that it is in principle covering the whole substrate, but by using stencils, so shadow masking, we can actually achieve patterns which it's very good, especially in this case for thermocouples, for instance. It is a very fast method, it's very reliable, it's easy to integrate in high throughput technology. We've seen in many fair trades that they integrated also in roll-to-roll facilities. It's a non-contact, non-destructive method, and it's an intrinsically additive method, so we are just stacking up, we're not removing material, which leads then to a reduction of the wasted material when we're producing something. Of course, we are not able to have very fine lines, so what we could achieve with lithography or with inkjet printing, you cannot do it with spray deposition. Which are the materials that we're talking about? They are normally nanomaterials, and the good thing about them is that we can synthesize most of them by ourselves in very simple lab facilities. For instance, you can synthesize carbon nanotubes with an ECCVD process. You can synthesize silver nanowires in solution. Same for PEDOT PSS. And we could employ all of them in couples, for instance, and exploit their difference in the thermoelectrical potential. The silver nanowires are not famous for their high Seebeck coefficient. Actually, they have quite a low one, but they're the best semi-transparent material that we could have access to, so best in terms of conductivity. So under this point of view, we chose that in order to then bring the charge to the other side of our structure. PEDOT PSS and carbon nanotubes, and in general carbon-based material, are on the other hand characterized by very good Seebeck coefficient. So what we do, we put in a solution, we spray deposit it on glass or on PET or on any plastic foil, and then we can see that they are semi-transparent. We analyze the spectrum, so what you can see there on the right side is the spectrum of carbon nanotubes, of silver nanowires, and PEDOT PSS. Normally, as a reference in literature, you use the transmittance at 550 nanometers, and you just give a number for that. For the layer thickness, we use the CNTs were the top performance, but the resistance of the CNT layers is also relatively high. This that you see here is another figure of merit that takes into account also this part. So it takes into account the shield resistance that for the semiconducting CNTs we used was 72 kilo ohm square. You can really understand from here that if we employ carbon nanotubes, we're gonna have most likely a very high voltage, but we cannot transfer power because the resistance is very high, and so the power transfer will be very low. So this is not perfect for energy harvesting, although it's great for sensing applications. Now, when we speak about printed thermocouples, we speak about structures that look like this. So this is, let's call it an N leg and a P leg, but it's very arbitrary. You can also call it leg A and leg B. And then you've got a hot side and a cold side, so you establish a temperature gradient between the two sides, and you harvest the voltage that is coming out from the first to the last leg. What we were doing was just using a shadow mask, and this is the final result. I've been talking about transparent thermocouples, and then everything is orange. Of course, it's because we used this material, which is called Kapton, and it is orange. We decided to use this material simply because we wanted to test it for higher temperature, and Kapton is famous for being very resilient to high temperatures. We were triggered by an automotive company because they wanted to have a similar device, and Kapton was the perfect choice. But of course, we've got fully functioning thermocouples also on PET, so the normal plastic that you see on your bottles, because our processes are below 100 degrees. So they're all in ambient conditions and below 100 degrees. For the characterization, we developed our own setup, which is composed of a heater and a cooler. It's stuck, I'm sorry. Yeah, which is composed by a ceramic heater and a thermoelectric cooler, and this way we are able to keep the temperature gradient. And there is a heat sink, of course, because we wanted really to achieve the 300 degrees in thermal gradient. In the end, we did not do it because one of the materials degenerate with temperature, especially PEDOT PSS loses all its properties above 150 degrees. The setup is fairly simple. So we got a PCB for the readout of the voltage, and we've got PT100, so it's thermistors to measure the actual temperature that we're having. Now, getting to the results, we did several trials, which are different combination of the materials that I presented early, and they are particularly the ones that you see in this table. So when I say first material silver nanowire and second material carbon nanotubes, I mean that literally from a chronological point of view, silver nanowires have been deposited first and carbon nanotubes later. You might think that it's the same because they're the same material, but at the end of the day, the results might be very different. And that is due to post-processing that you need to apply to the materials because of them functioning. So for instance, carbon nanotubes need to be, they are immersed into a polymer matrix that needs to be removed after the dispersion. And so this could somehow affect also the underlying underlaying layer of silver nanowires. The same for silver nanowires. They have an insulating agent called PVP that has to be removed before it can really work out. PEDOT PSS needs a thermal annealing, and this could affect somehow the results also of the underlying material. The best combination we were able to achieve was with silver nanowires and CNTs. In the combination, first silver nanowires and then CNTs. It's not entirely clear why. We've been really thinking about it, reading into literature. We reiterated the experiment several times. That's the advantage of having master students helping you out. And we were consistently having the same results. Our best thought is that by depositing the CNTs after the silver nanowires, we're somehow having a better interface, and that could be due to the fact that we need to put CNTs in water in order to remove the dispersant, and that also helps to clean up the silver nanowires from the PVP. Concerning a measurement against temperature, you can see it in the next slide, and we'll show that as a differential temperature sensor, it is quite linear. Regardless from the couple of materials that we decide to use, it works fairly well. Concerning the sensitivity, we're speaking of 50 microvolts for Kelvin, which is pretty decent, and sensitivity is above 98% until 110 degrees. I did not present the plot until 110 degrees because, as I was saying, the PEDOT PSS would stop functioning, so that would not be a fair comparison. But for sure, you can see that the silver nanowire carbon nanotubes couple, regardless from the combination order, they are the top performers here. Now I will get to the conclusions, and what we've seen is semi-transparent thin films, thermocouples. Their transmittance is about 80% at 550 nanometers. We spray coated them on flexible substrate. It's an easy to upscale process. We were actually very happy with the results we had in the end. The real problem I could see, besides what I already said on optimizing, like also optimizing the geometry and optimizing the materials, the real problem is that we need lower resistance if we want to have energy harvesting. But as a sensor itself, that's I think it's perfect in this resistance range. Thank you.